hello everyone. Yeah, we are going to talk about do-it-yourself mock. So in other words, we are going to do everything ourselves that usually the MetaObject compiler does for us. I mean, that immediately prompts the question on why. I mean, just because we can is probably not a good enough explanation, especially when we have to sell this to our bosses. And as most do-it-yourself projects, that's going to be rather messy and not the same quality as the automatic stuff. So yeah, it's worth looking at why we are doing this. Because usually, I mean, mock is very well hidden in the build system. We only have to add the QObject macro, and everything else just works, right? It's not getting in our way. One of the major issues with the string-based connects has been addressed in Qt 5. So we now also have compile time checked signal slot connections. I mean, what else could we possibly want to, so that it motivates us to do this ourselves and instead of letting mock do it? I mean, one reason, of course, is if we do it ourselves, we learn how this actually works, and this enables us to write better code, to help us to debug specific problems in there, because we actually know what's going to happen, and it allows us to write faster code, maybe. But that's still, like, just because we want to know, still not a very good reason to dig into this. But there are actually some. So the major limitation of what mock gives us is it requires us to know the object layout at compile time. So we need to know what properties does the object have, what signals are in there, what slots are in there, what types they have, and so on. Usually we have that. But there is a few examples where this is not the case. Let's take, for example, inter-process communication. So we can make assumptions on what a remote service offers us in terms of API, but we will only know for certain once we connect to it, so at runtime. And then we see, is this method actually available, or what properties are offered there. So it would be nice if our object layout actually reflects what's actually available on the remote side rather than our compile time assumptions. And another big topic is scripting. If you define an object in QML, you can add properties and slots and signals. But that's, of course, you only know about that at runtime when the actual script file is passed. Same with integration with Qt script or web technologies. And also the other way around. So if we have a large amount of C++ objects that we want to export to a scripting language, writing all that manual boilerplate code to wrap it in a QObject so we can export it, way too much work. And I mean, this is not just theoretical examples. We find several use cases for that in Qt alone already. We have debus for inter-process communication. That makes heavy use of the stuff we are going to see. The Qt remote object system that Björn was showing in his lightning talk yesterday, actually a new module in Qt, has exactly the same requirements and the same needs. Then we have a bunch of scripting languages or integration with scripting stuff in Qt, QML, Qt script, all the WebKit stuff. And there's like somewhat less obvious use cases like QSignalSpy. That's a nice little helper class in QTestLib. It allows you to connect an arbitrary signal to it. Could be from your own class with your own custom types, doesn't matter. And it will tell you if that signal was emitted, how often it was emitted, and it allows you to, or it gives you the arguments that were actually in that signal. But how would you implement that usually with the normal mechanisms you have available in QObject? So what we want in all of those cases is the ability to, at runtime, say, this QObject should have a slot with this signature, these arguments, this return type. We want to have a signal in this object, or we want to have properties of a specific type in this object. So is this possible? Well, obviously the answer is yes, because otherwise that would be a rather disappointing presentation here, and we would be done at this point. So we are going to look at how this is possible, at what costs, or what are the issues. And for that, we are going to look through how this, what mock currently does, and how the static stuff work we are going to use, or we are currently using every day. And that's basically three parts. That's the QObject macro, which is the injection point into our class where the mock-generated code is integrated with the code we have written by hand. Then there's QMetaObject. That's the API for introspection. So that's the thing I ask, which slot do you have? Which signal do you have? What's the properties in this object? So that's, of course, relevant. And the third bit is QMetaCall. That's a method generated by mock. And that defines the behavior. So any incoming call to a slot or incoming signal, any property operation goes through that. So that's the point where we can influence the behavior. Okay, so let's start with that. QObject. So QObject is a macro that injects a number of member variable and method declaration into our own class. Some of this is shown here. I simplified it a bit and removed the stuff that is either boring or irrelevant for the stuff we are doing here. So essentially we have a few things to look at. The first one, static const QMetaObject, that's like a compile time static variable. And that's kind of the worst case problem we could have for doing something at runtime, because that's unchangeable and defined at compile time. Luckily, it turns out this is largely irrelevant for our case, because anything defined at compile time will not be used for dynamic stuff at runtime, so we can actually ignore most of the static stuff. Then we have a virtual method that returns the MetaObject dynamically at runtime, so that's easy enough to implement, right? So just a virtual method. Same for the other two, MetaCast and MetaCall, so for behavior and casting, regular virtual methods that we can override. So that's an easy enough entry point for us. And then there's more stuff, static method. Same thing there again. Anything that is static is a problem because we can't dynamically change that at runtime. But anything that is static means that at compile time somebody is deciding to use this. And I mean, if we don't know yet how the object looks like, there can't possibly be any code deciding at compile time like what method to call or so on. So it also turns out we can ignore those bits for our use case. So in the end, this boils down to that there's three virtual methods which the QObject macro declares, and then mock generates an implementation for that. And if we want to do this ourselves, that's the part we are going to do. Okay, then the second part, QMetaObject. Right, we saw the virtual method that returns the MetaObject. That's what you use to introspect, to find out at runtime which methods, which slots, and which properties exist. If we look at the API documentation, we again find lots of bad news. It's purely read-only, right? We only have getter methods in there. So you can query all kinds of stuff, but you can't change it. And there's also no virtual methods. So we can't just inherit from MetaObject and return our own stuff there. But as usual, the documentation is only telling us half the story. So it's always worth looking into the code and see the bits that the documentation tries to hide from us. And what we find in the code is QMetaObject is actually a struct, which means everything in there is basically public. And there's 3 relevant member variables in there. And since they're public, we can change them. And, the first one looks easy enough, right? That's a pointer to the MetaObject of the base class. So we can decide from what object we are going to inherit. And then there's a string table and some offsets into the string table and some data that describes how many methods we have, how many signals we have, or what type the properties are, and so on. That's usually, if you look in the mock-generated files, you see those large string tables and tables with random numbers in them. That's what goes in here. There is no magic in there, but it's not documented. Right, we could reverse engineer that and then just fill in the data structure, and we would have our dynamic MetaObject. So lots of work, but not something that would technically prevent us from messing around with this. So then we have the third part, QMetaCall. So that's, as I said earlier, the thing that defines the behavior, and it's one of the virtual methods that mock generates. And in there you see basically the dispatching of calls based on a method index that then call the actual implementation of your method, or that if you do a generic property access, it calls the getter method you defined in the QProperty macro. So just big switch statements that, depending on the input, forward to some other methods. You get 3 arguments in there. One defines the type of the operation. That's stuff like reading a property, writing a property, invoking a method, and so on. You get some kind of index that tells you which method or property this is referring to. And then you get a void pointer array for operation-specific arguments. I mean, it's not really nice API to work with. You have to handle void pointers in a safe way, but in the end, I mean, it's a virtual method we can override and do our own stuff in there, right? So that's also looks doable. Right, and we have MetaCoS. That was the third virtual method that we saw of the QObject macro. That one is actually completely boring because what you get as input is just a name of the class you want to cast to. So all you need to do is check if your name matches that string exactly, including all the namespaces. And if so, you return this. Otherwise, you pass this on to the base class. It's 2 lines of code, so we won't look at this any further. Okay, so what we have seen so far is we should be able to replace everything that mock usually does with our own code, and we can, there's nothing in there that forces us to make this compile time static, right? So it's virtual methods and data structures we can change at runtime. So we are getting in the right direction there. So then let's now have a look at how can we actually implement this. So what we want to achieve is we want to have a QObject that behaves like a QObject. You can connect to methods and signals. You can interact with the properties. You can expose it to, say, QML, and it will behave exactly as if you had static properties in there. But we want to be able to, at runtime, say, these are the methods we want to have in there. These are the signals we want to have in there. These are the properties with this type and that notify signal and so on. And yeah, the approach will be, we will create our own MetaObject. So just as we've seen, we will fill those via data tables, and we'll see there's actually a much nicer way of doing this. And we'll implement our own QMetaCall method to give it some behavior. Right. And instead of reverse engineering all those data tables, there's actually a class for that in Qt that does exactly that, and that's QMetaObjectBuilder. If you haven't heard about that, it's because the documentation doesn't tell you it exists, because it's private API. But since the module split in Qt 5, all the private headers are fortunately installed, which is awesome, and we can use a whole lot of this stuff. If you look at MetaObjectBuilder, you'll see that the API is largely symmetric to QMetaObject. So it basically has all the setter methods that we are missing in QMetaObject itself. So just see the most basic example. We create an instance of the MetaObjectBuilder, and then we can set a class name, and we can set the base class, just pointer to a QObject. However, there is probably a reason why it is private API. It doesn't do any sanity checking, like you might expect or you're used to from regular Qt classes. So if you try to do this and you forget to set a base class, or you give it a class name that contains non-ASCII characters or spaces, I mean, it will happily accept that. The problem is that what you get out of it might show very interesting behavior. So, I mean, there isn't even asserts in there that make sure that the input is at least somewhat valid. So you have to be very careful there. So what we have seen so far, we can create a class, set the base class, set the class name. So now it's about adding some properties. For that, there is a class called QMetaPropertyBuilder, which, similar to the MetaObjectBuilder, is basically the symmetric API for QMetaProperty. It has all the setter methods that we are missing there. The way you use this is, given a MetaObjectBuilder, you just call add property, you give it a name, you give it a type, and then you get the property builder back, and you have setter methods for everything that you're used to from QMetaProperty. Same thing here. There is no sanity checking. So it's your responsibility to make sure that you specify a type that actually exists and that QVariant can handle. A typo in QString, then it will just not work at runtime. Or a notify signal that doesn't exist, right? You can put in arbitrarily wrong stuff there. It will not complain. Basically the same approach for the API also exists for methods. So there's QMetaMethodBuilder, which is the symmetric API to QMetaMethod. So all the setter methods we are missing there. There's a number of methods to add them. Method is just, that's the counterpart to what you usually define as QInvocable. Add signal, right, that's for signals. They default to a void return type. For methods, you can actually specify a return type. Slots is technically very similar to methods, just that you're allowed to connect to them. And constructor, I think that's from Qt script, that's rarely used nowadays. But in the end, that's how you can add methods, and the MetalObjectBuilder has all the API to set additional properties on them. And you can specify the arguments, the argument types, and so on. Also here, there is no sanity checking or at least basic intelligence in the class to avoid common mistakes. So you have to do it exactly the way this needs to be done in order to work. And the most tricky pitfall here is you need to have a specific order based on the type of the methods you're adding. And that means all signals have to go in first, and then everything else. The reason for this is there is an optimization in QObject that assumes that all the methods are ordered in this way. So if you're looking up a signal as part of the connect statement, you can stop searching once you find the first non-signal. But if you order them randomly, you will be able to connect for like the signals that happen to be in front, but everything else might fail. So, while at the same time, if you look at methods in general, you will see all of them. So you look in a tool like Gamma Ray, you see all your signals are there, and then Connect tells you, I can't find the signal. So it's a lot of fun to debug this. Try to avoid that. Make sure you call add signal first, and after that, you can add all the others. Also something to keep in mind, if you have notify signals for your properties, you also need to make sure that you run them before creating all the other methods. Right, and there's more. So basically anything that exists as QMetaSomething, there is a corresponding QMetaSomethingBuilder. So you can add enums and class info and anything else you find in a MetaObject. I mean, enums are still kind of useful, especially if you're coming from IPC or scripting where there is the concept of enums. Class info, that's just for arbitrary extra textual information, so that can be also quite useful. The static MetaCoS stuff, that's for currently mainly used for the static connects. That's something that is largely irrelevant in a dynamic scenario, because you can't possibly do function pointer connects for functions that you only define at runtime, right? So they simply don't exist, so you can't get their address to connect to them. Okay, and once you're done with adding all the stuff that you want to have in your MetaObject, we can call toMetaObject, and we actually get the completely assembled QMetaObject out of this. At this point, it's read-only, but it has exactly the same data tables in it as mock would usually generate them for you. Right, and then it's just a matter of integrating that in our class. But that's as easy as just returning it in the virtual MetaObject method, right, that the QObject macro defines. There's still one more tricky bit. You have to clean this up at some point. Usually the MetaObjects are compile time static, so it's read-only data. You don't have to delete them. But now that's no longer the case. And one might expect that this is just calling delete. But if you look at the implementation, you see it's doing raw malloc calls, so you have to free it with free. Otherwise, you have Valgrind complaining, and depending on the platform, it might even crash. So But with all of that, we get in QObject where we can define at runtime what methods we have in there, or what properties we have in there. And if you introspect it with the same means you can introspect a regular QObject, you won't see a difference. Usually you want to do that construction part relatively early before your object is used, especially when QML is involved. Because QML does some very heavy caching on the MetaObject information. So if you change the MetaObject once QML has seen it, those changes might not necessarily be reflected in QML, and you might get all kinds of other interesting behavior. So in general, I mean, it's dynamic in the sense that you can decide at runtime what's in there, but I suggest to avoid trying to change it while the object is alive. So you make up the layout of the object, you add the meta object, and then you keep it static while the object is alive. So we have the introspection, but yeah, I mean, that means we can, for example, connect to the methods and or the signals and slots that we have just defined, but nothing will happen. Or we can read properties. We see the properties in QML already, but I mean, reading them just gives us nothing. So we still have to give this some behavior. And for that, we have to look in the implementation of QMetaCoS. As we've seen earlier, the first argument tells us the type of operation we are dealing with. We are going to look at the three most important ones here. There's actually a lot more than the ones here, but the important ones are reading a property. So this is when you call the property method on QObject. So of course we have to find out the value of that specific property and return it somehow there. There's write property, right, which is the counterpart. If you call set property on a QObject, you end up there. And we have to store it somehow or pass it on to whatever we are actually representing here. And then the somewhat more complex one is invoke meta method. That's where we end up if you call invoke method or if there's an incoming signal that is connected to one of our slots. So this is basically to handle method calls. Okay, then let's have a look at how those would be implemented in detail. So the second argument in MetaCoS, that's the index of the thing we are dealing with. And the way this is handled, both for properties and methods, is if that value is less than the amount of properties we have, it's basically a zero-based index into our properties. So in that case, we handle it and we return a negative number to indicate that we did handle this. Otherwise, we subtract the amount of properties we have. That's basically rebasing it onto the index of the base class. So having a zero-based index for properties in the base class, and then we return that. And then QMetaObject internals that are actually calling us here will recognize this and call the MetaObject of the base class. So we don't ourselves call QMetaCoS of our base class. That's done outside. We just have to adjust the index, rebase it on to be zero-based for the base class. It's a bit weird initially because it's not the way you would usually expect virtual methods to work. But it's kind of necessary in order to allow arbitrary inheriting so that objects don't need to know who inherits from them or what they are inherited from. And the base class can change their indices and so on. And then we have this void pointer array. And that it requires a bit of digging through the code to find out what the individual elements in there actually are supposed to be, because none of this is really documented. So for reading a property, for reading and writing a property actually, the first entry, that's a pointer to the actual data. So for reading, this is pre-allocated storage for the type of that property, in which we are supposed to write the actual value. If we are receiving the value, it's a pointer to just the value. And then the third entry, not the second one, that's a pointer to an integer for the return value of said property. That's by default set to -1, which would evaluate to true, so you don't have to change that if your set property call always succeeds, otherwise you just have to set it to 0. The reason why there is a gap in between is this guy. It's commented with, this is only used by debuggers and don't touch it. So that was Thiago. Yeah, but apparently that's somewhat specific to debuggers, and the comment explicitly says don't rely on this. So we ignore this. Right, so now pointers to, or void pointers to random data is a bit, annoying to deal with. So if you know exactly what type your property is of course you can just forcefully cast that to the specific type and then assign the value or just read out the value. But since we are building something dynamic, right, we need something more generic. In most cases, you don't know the exact type, and you don't want to write large switch statements with, if this is an integer, then do that, and so on. Most of the time, we are dealing with QVariant. And luckily, there's infrastructure in Qt that allows us to convert to and from like raw void pointers when dealing with variants. So when receiving values, that's very easy. There's a constructor for QVariant that just takes the void pointer. And of course, it needs the identifier of the type. So that's an integer provided by QMetaType. So it knows what that, or how to interpret that void pointer. That type ID you usually get from your MetaObject. That should know it. Otherwise, there's QMetaType that you can ask if you only have a string of the type or so to get you the ID. When returning values, we usually have a QVariant containing that value. So we have to create a copy of that into pre-allocated storage of the specific type. And for that, we have QMetaType construct, which, given the void pointer that's actually pointing to the data stored in QVariant, and the type ID and the location of where it should create the copy into, will do just that. And you need to actually call that method. Otherwise, if you just assign that pointer to this pointer, right, you have two instances that will, in the end, try to delete it, and that's just going to crash. And of course, I mean, that would be too easy, so there's a special case. If the type of your property is actually a QVariant, you don't get but you get a pointer to the variant directly, so you need to special case that you don't like copy like the content of a variant that is again a variant into a variant. So otherwise you keep nesting them. So you need to like shortcut that and copy that directly. So typical code has like those kind of approaches for anything that's not a variant, and then direct casting in case you are dealing with a variant. I mean, assuming your properties can be a variant in the first place. Not all backends might actually support that. Right, and then we have the second part, calling methods. the way that that methods are addressed works exactly in the same way. So you have a zero-based index for all the methods you have in your object. If that's out of range, you rebase to the index of the base class and you return that. For the arguments, it's slightly more straightforward here. The first one is the return value. So this is again pre-allocated storage of the exact type of the return value in which you write the result in the same way as we have seen it earlier. And everything after that is the actual arguments with which the function is called. All those void pointers usually are very transient and become invalid as soon as you return. So if you need to store them for later processing or passing it on to some other system, you need to create actual copies. And the meta-type methods, similar to what we've seen earlier, given a type ID, allow you to actually manage copies of that. So that can be quite handy in this case. And then another common scenario there is turning the entire argument list in a list of variants. Because you don't want to store the original. You have to copy it, and you want something that is introspectable. Or generic enough so that in case you don't know the specific types. So the general approach is you iterate over all the arguments, which means you need to know how many there are. Your MetaObject should know that. You determine the type ID. Again, your MetaObject should know that. There's one special case, that's the signal spy I mentioned earlier. We'll see that actually doesn't have a MetaObject that knows the exact slot signature. But for incoming signals, you can actually query the sender object or the MetaObject of the sender and see the signature of the signal that you just received. And that also tells you what the arguments are supposed to be. And then similar for, as we've seen for properties, you can use qvariant, given a type ID and a void pointer, to create a copy. And then you have something that is generic and that you can deal with. Right, so there's one more missing bit. We can receive signals, but we can't emit signals yet. Usually mock generates us like stub functions that have the same name as the signal, and that I can just call with the macro emit in front if I want, but technically it's just a method call, and they will emit the signal somehow. I mean, we can be connected to, you can do signal-to-signal connections, so the infrastructure is all there. We just need a way to actually emit the signal. And the way to do this is, again, an undocumented function, MetaObjectActivate. Right, you give it the specific instance of the QObject, you give it the MetaObject, you give it the index of the method or the signal, which you can look up in the MetaObject, and then void pointer array to the arguments of that signal. And that's exactly what mock would generate you in the function stubs for the signals it generates. So if you get an QMetaCall call invoke method for a signal, your typical implementation would just pass on the stuff you get to activate, so it actually emits the signal. So this way you enable signal-to-signal connections to work. Another use case where you probably need that is if you have notify signals in properties. That's also in mock-generated code. So if you want to support that, you have to implement that yourself as well. So if you see the write property call, you should check if the property has a notify signal, and if so, you call activate to call all the slots connected to the notify signal. Right, and then there's a bunch of stuff we skipped in MetaCall. There's a whole bunch of more operations to deal with properties, query individual properties of them, reset them, and so on. That's fairly straightforward. It's exactly the same as read and write as we've seen. And there's a few operations like registering meta types and finding the index of a function pointer, which again is largely used for static connects. And that's something that doesn't work with dynamic objects anyway. So that's very uncommon to be implemented in this case. Right, so now we have a QObject. It's introspectable, and it behaves like we would expect. So if you have an incoming signal to a signal, that's emitted. If you change a property, notify is emitted, and so on. The way we can interact with that is purely from the C++ side, purely the generic API in QObject. So this is getting a property, setting a property based on a string name. It's a string-based connect, right? We can't do the function pointer connects. And there's the invoke method function, which again, given the string name of a method, allows us to call a function. That's, of course, not how we want to really interact with C++ objects. And that's why most of the IPC systems have a code generator that then again turn this in actual C++ functions. But if we expose this to QML, you don't see any difference, because this is all string-based anyway, right? The whole script is a string that is evaluated at runtime. And that's where the real power of this is, right? So if you're dealing with QML or any other scripting language, and you need to expose C++ stuff to there, you write a few hundred lines of somewhat complex generic code, but it will just map everything in one go to QObjects that behave exactly as if you had written thousands of lines of boring QObject wrapper code. So that's where the real power is. But yeah, you can push this one little step further. And that gets us back to QSignalSpy. If you remember there, you can connect an arbitrary signal to the signal spy, and it then will record any incoming signal. The problem is, at the time of connect, we are notified about this, so we can't add a matching slot to our MetaObject in time for this to work. And connect checks if there is a corresponding slot that actually is compatible, right? Otherwise it fails. But there is a way around this. There is, again, an undocumented connect method in MetaObject. It's index-based, so you have to do the lookup yourself, but it doesn't do any safety checking. So you can connect an arbitrary signal to your object, bypassing all the safety, and you just specify an index of the slot it's connected to. If that slot exists or not, doesn't matter. You just get that index in your QMetaCall implementation. And I mean, there is nothing that forces us to interpret that in the same way as mock usually would do, right? So we could just, look at where is that signal coming from, convert the arguments, and I mean, that's exactly what SignalSpy does. It bypasses all the safety, it interprets the index in its own way, it looks up in the sender object how to interpret the incoming call, and you have a very powerful and generic signal interceptor. And I mean, there's more use cases for this. Right, there's QSignalMapper that currently can only handle one signal per object, and it can't evaluate the arguments in any way. If you need something more powerful, this is the the toolbox you have to build this. Right, but there's of course the question, is this all safe, right? We are using private API and bypassing a whole lot of safeties in there. Olivier, who had the talk before me here, was actually complaining yesterday that I showed this to people because it might get them to do stuff that will break with changes he's going to do. But if we look at what actually happens here, all the methods we are calling, all the data structures we are generating is exactly the same that mock does. And mock-generated code is part of our application. So Qt can't change that interface because it would break backward compatibility. So as long as we only do stuff that mock does, we are safe. And that's actually all of this with the exception of MetaObjectBuilder. They could, in theory, remove that in a newer Qt version. But it's used in several places in Qt, so that's rather unlikely. And if it's removed, it's likely to be replaced with something far better that you want to use anyway. But if you want to be really on the safe side, you could just copy that into your code. I mean, it generates data structures that are kind of covered by the ABI guarantee. It depends on a couple of other internal headers, but nothing too big. So if you want to be absolutely sure that your code still compiles with Qt 5.6 or whatever, some new version, without having to adjust your own code, that might be a way to deal with this. Also, I think that's a pretty low risk. So most of this is actually safe, and it's actually used in several places. So what I wanted to show you is that QObject is actually even more powerful than what the documentation advertises if you dare looking into the internals and actually do some of the stuff yourself. And I mean, there's plenty of use cases for this. Anything interacting with dynamic languages, anything that is only defined at runtime, like IPC systems. We are seeing several like QML-based domain-specific languages appear. That's where this can come in really handy. And I mean, generic signal interception, there's signal spy, signal mappers, tools like gamma ray. There's just a lot of stuff you can build with this. Yeah, I think that's it. Thank you.
Thank you very much, Volker. Is this working? Hello? Right, good. Thank you very much. We've got some time for questions now. If you want to ask a question, please put your hand up. Let me get to you with the microphone, and then Volker can answer. We'll repeat.
So this is all based on private APIs. And so if you build a system using those APIs, you have no guarantee that in future versions of Qt, they might have the same signatures and everything, or classes will even exist. So should we really invest in that? Do we have any sort of guarantee about how stable this is?
Yeah. Well, there's, of course, no guarantee for Qt 6, right? Anything can change there. For the rest of Qt 5, there is the guarantee that the ABI won't change in the way that an application you build with an older Qt 5 version will break with a newer one if you just update the Qt version. And most of the stuff we are using, with the exception of MetaObjectBuilder, is using private API, but it's private API that the mock-generated code that's part of your application is using, right? So if they would change that, they would break their ABI guarantee. And I mean, that could happen by accident, but it's not intended, right? Well, it has never happened before. And I mean, there's precautions in there to deal with this. The data structures in MetaObject have a revision number, so it can be extended without breaking backward compatibility. So all of that should be safe. The only one that is a bit problematic is the MetaObjectBuilder itself.
Okay, I'm sure Volker will take questions if you come up at the end anyway. Okay, so another round of applause, please, for Volker.